These are the notes for AP Calculus on the topic of trigonometric integrals. So we're going to look at the 6 basic trigonometric integrals, which might look familiar if you look at them carefully. The integral of cosine x is sine x plus our unknown constant c. And that's because, remember, the derivative of sine is cosine. And then the integral of sine x is equal to negative cosine x, because the derivative of cosine is negative sine. So those are the reverse of the derivatives of those. And then notice the integral of secant squared, secant of x squared equals tangent x plus e, because the derivative of tangent is secant squared. So these are all really just the reverse of the derivative formulas of the basic trig functions. Now remember, on the derivative formulas, an easy way to remember if the answer, the derivative of a trig function was positive or negative, was based on if the original trig function started with a letter C. All the ones that started with a letter C were negative. All that didn't start with a letter C were positive. Well, for these, it works in a similar fashion. Let's look at all the ones that are negative here. Except this time, what you'll notice, it's not that the original function starts with C, because this one is sine, right? And it gives you a negative cosine. It's that the answer starts with C. So if the answer starts with C, cosine, cosecant, cotangent, then the integral or antiderivative is negative. But then take a look at all the answers that don't start with the letter C, secant, tangent, and sine, and those are all positive. That's one way you can remember which ones are positive and negative. If the answer starts with C on antiderivatives or integrals, then you know it's negative. But I organize these in another way so you can see some other patterns. Sine and cosine are the easiest ones, obviously. You just don't remember if it's negative or positive. The other ones, notice, secant squared is tangent x, and cosecant squared is negative cotangent x, so those are kind of similar. Secant x tangent x is secant x, and cosecant x cotangent x is negative cosecant x. All right, so let's see how we use these in conjunction with the other integration rules we've learned thus far. So this first one just says evaluate the indefinite integral. So notice these are just added and subtracted, so we can integrate each one separately. And the variable here is theta. So we got 2 stays out in front. When you integrate sine of theta, that's cosine theta. Notice it starts with a c, so it's going to be negative, which gets multiplied by the 2 to make it negative 2 cosine theta. Then we have negative 3. Integral of cosine theta is sine theta. Sorry about that. So we'd have sine theta. And then theta squared, having x to the variable theta. When you integrate that, that's just a power. It would be plus theta cubed over 3. And then minus pi, well, pi is a constant. So it'd be negative pi theta. Just like if it was 3. It'd be 3 theta, and then plus our unknown constant. Okay, let's take a look at the next one. Now in this one, it's more complicated. We've got integral of cosine t divided by the square root of sine t dt. So this involves, it's way too complicated to integrate in this form, so we need to use substitution. So if you look for the function inside, you can see that sine t is inside the square root. So we'd say u equal to sine t. And that allows us to rewrite our integral as we still have cosine t on the numerator. Divided by, now we could write it as the square root of u. since we say u equal to sine t. But we're going to, again, try to get this all in terms of u. So this time we have to get rid of the dt. And the way we do that is by taking the derivative of what we say u equal to of our function side. In this case, it'd be du dt instead of du dx. The derivative of sine, remember, is just cosine. And then when you solve this for dt, multiply both sides by dt, end up with du equals cosine t dt. And then we divide by cosine t to solve for dt. You end up with dt equals du over cosine t. And then we can substitute that in for dt there. We would have du over cosine t. And then notice what simplifies here. The cosine t's reduce out. So we're just left with 1 over square root of u d. In this case, there's no constants to pull out in front. So to make it easier to integrate, rather than writing it 1 over the square root of u, switch it out of radical form. Be u to the 1/2, but it's on the denominator, so when you move it up, it becomes u to the negative 1/2. U. And then we can use the power rule for integration. So when you integrate that, that becomes u to the positive 1/2. But instead of dividing by 1/2, that's the same as multiplying by 2. And then we need our unknown constant plus c. And then we could write that as 2 squared of u plus c. Switch it back to radical form. And finally, we got our answer back in terms of the original variable, which in this case is t. So we can take our sine t here, is what u equals, and substitute that back in for u. So our final answer would be 2 square root of the sine of t plus c. Okay, let's take a look at a couple more of these. On this one, notice we've got x secant of 7x squared tangent of 7x squared dx. So again, way too complicated to integrate in this form. So this time, notice there's one function inside. In this case, it's 7x squared. It's inside both secant and tangent. So if we say u equal to 7x squared, then we can rewrite our integral. We still have the x there. But now we can write it as secant of just u, since we say u equal to 7x squared, and tangent of u. And then we don't want the dx in there, we want to get all in terms of u, so that's why we take the derivative. Du dx is root of 7x squared is 14x. And then when you multiply both sides by dx, we end up with du equals 14x dx. And finish solving for dx, divide by 14x. So du, so dx would equal u divided by 14x. And again, we can substitute that in to replace our dx right there, to get it all in terms of u. So we have du over 14x. Then, do you see what would simplify? We've got our x's there on the numerator number. Those are reduced out, which is what we want. We want all in terms of u. In this case, we can pull out a constant of 1/14. And then we're just left with the integral of secant u tangent u du. So then secant u tangent u, that's one of our new integrals. Remember, that's reverse. That gives you, remember, it's secant x tangent x, it's secant x, it's secant u tangent u would be secant of u. Remember, it's just the reverse of our derivative formulas. And then plus c. But that's not our final answer. We want it back in terms of our original variable x, so we take the 7x squared, substitute back in there. So we have 1/14 secant. You don't have to put parentheses, but it does make it look a little easier to see what's inside secant if you do. Secant of 7x squared plus c. All right, let's take a look at the next one. The next one's a little bit trickier if you're not careful because we've got two functions inside. It's too complicated to integrate like this. We've got cosecants inside the squared and cotangents inside to the 5th power. So you could think about setting u equal to either cosecant. So let's try our two possibilities here. Equals cosecant x, or u might equal cotangent x. Well, the way you can tell which one's going to work is based on the derivative. You say u equal to cosecant, the derivative would be negative cosecant x cotangent x. But if we say u equal to cotangent, the derivative would be negative cosecant x squared. So the way you can tell which one's going to work is based on which one's going to be able to get rid of all the x's, get the integral in terms of u. If we say u equal to cosecant, we'd have u squared, but then we'd have this cotangent to the 5th. And negative cosecant cotangent, that's not going to cancel out cotangent to the 5th. So that one is not going to work. However, if here we said u equal to cotangent, the derivative is negative cosecant squared, we'd have u to the 5th, and notice there's a cosecant squared that can help us cancel out this cosecant squared. So that's the one. That's how you can kind of tell which one is going to work and which one's not. So if we multiply both sides by dx, we have u equals negative cosecant squared x dx, and then divide by cosecant squared. So we have dx equals du over negative cosecant squared. So we can rewrite this integral. Of the cosecant x squared and then we say u equal to cotangent, so that's going to be u to the 5th, and dx we just figured out is du over negative cosecant x squared. So you can see this time the cosecant squareds are going to cancel out. We can pull a negative on the outside, and then all we're left with is u to the 5th times du. So now we've turned a more complicated integral into a simple one. So again, we have u, sorry, negative, and then u to the 6th over 6 plus c. And then just substitute in what we said u equal to. Remember, the one that worked was setting u equal to cotangent. So negative So tangent x to the 6th divided by 6 plus. So those are some cases with using trig functions with u substitution. Now let's take a look at a couple where we have to separate the variables. So let's find the particular solution, which means we're going to be able to solve for y equals f of x. We're solving for y with an initial condition f of 3 is 2. So first we have to separate the variables. Since the derivative of fraction, you will cross multiply. Is your first step. So you have 3y squared dy equals sine of pi x cross multiply. And in this case, they're already separated. The y to the y, the x over the x, so we can just integrate right both sides. The 3 just stays out in front. And we integrate y squared, you get y cubed over 3. But notice on the right side, we can't quite integrate yet because it's not a function inside. Sometimes you have to use u substitution on these separation of variable things. So here we'd say u equal to pi x. Then du dx, rid of pi x would just be pi. Multiply both sides by dx, so to get du equals pi dx. And divide by pi, so dx equals u over pi. So this one, we haven't integrated yet, we can rewrite as now the sine of u. And then we just figured out dx is du over pi, so we can put that in. Okay, and then on the left side, you can see the 3's reduce out. Get y cubed equals. Now the 1 over pi, you can just plot in front. Okay, and then when you integrate sine, that's negative cosine. So it'd be negative plot in front, and then plus c. But we're not quite done on the right side because we still have to substitute in the pi x. For u. So now we have y cubed equals negative 1 over pi is the cosine of pi x plus c. Then to find c, remember we're given this initial condition, this is the point 3, 2. So there's your x and there's your y. So we can just substitute those in for x and y. So y we have 2, so that'd be 2 cubed equals negative 1 over pi. Cosine of pi x. Oh, sorry, not pi x. That's going to be, when you plug in 3, that's going to be 3 pi. Plus c. So 2 cubed gives you 8. Sorry about that. Equals cosine of 3 pi is -1. That's the same place as pi. So that's a -1 times -1 over pi just gives you +1 over pi plus c. So then you just subtract that over. So c would equal 8 minus 1 over pi. And then we can take that c value and substitute it right back in here. So then we just have y cubed equals -1 over pi cosine of pi x. And we just figured out c is +8 minus 1 over pi. And then last step to solve for y would just be to isolate, to take the cube root of both sides. So you get y equals, and since we took an odd root, you do not need plus or minus here. Cube root -1 over pi cosine of pi x plus 8 minus 1 over pi. All right, let's take a little one more, where we have to separate the variables with a trig function. But this one's an applied problem. So it says, let v of t be the velocity in feet per second of an elevator at time t seconds. The velocity of an elevator satisfies the differential equation dv dt. With this initial condition, v of 1 is 3 pi over 2. Find an expression for v in terms of t. So we're trying to find basically the velocity. And notice what we're given, dv dt. Well, that's the derivative velocity, which we often call acceleration. So what we're really starting with, this is really the acceleration function. And we're trying to work back to the velocity function. Remember, previously we learned that the derivative of velocity gives you acceleration. So now with integration, we're able to work backwards, starting with acceleration and working back to velocity. So again, if we first go by cross multiplying, we'll get cosine of v dv equals 3t minus 4 6 dt. And notice in this case we don't have to divide anything. This variables are already separated. We can integrate both sides. When you integrate cosine, you get sine. It doesn't start with a c, so it's positive. Sine of v equals, well, you could multiply this out to the 6, but it's much easier if you just use u substitution and set u equal to the function inside, which is 3t minus 4. And then take the derivative. Then we can rewrite this as just u cubed, sorry, u to the 6th, I mean. And then when we take the derivative, du dt, the derivative is just 3. So then dt equals du over 3. We're going to multiply by dt and divide by 3. So we can substitute that in there. So you have sine of v equals, we can pull out the 1/3. And then when you integrate u to the 6, we get u to the 7th over 7. Let's see. So if we simplify that, we have sine of v equals, that'll be 21, and you also need to plug u back in. So let's do that at the same time. 3t minus 4 to the 7th over 21. Let's see. So now we need to find c, and notice they give us a point on the velocity right here. In this case, though, instead of x and y, notice it's v of t. So the 1 must be the t. We have the point 1, 3 pi over 2. So 1 is our t, and 3 pi over 2, that's our v. Since the 1 is in parentheses, and so is the t. So if we substitute that in for t and v right here, we'll have the sine 3 pi over 2 equals 3 times 1 minus 4 to the 7th over 21 plus c. So sine of 3 pi over 2, that's a negative 1, equals, that's 3 minus 4 is negative 1 to the 7th. This is an odd power, is negative 1, 21, plus c. And then if we add 1 over 21, we get c equals, well, that's negative 22, sorry, negative 21 over 21. Same as negative 1. Plus 1, that's going to be negative 20 over 21. And then we can substitute that right back in here. So now we've got the sine of v equals 3t minus 4 to the 7th over 21 minus 20 over 20. The last thing we have to do is find an expression for v in terms of t. Notice, in other words, solve for v. So to get rid of the sine, you can't divide by it, which is because v is inside sine. But what you can do to get rid of sine is take the inverse of sine, which sometimes it's written as this, especially on many calculators. But another way it's written or called is arc sine. So we take the arc sine of both sides. So the arc sine of sine c equals the arc sine of this. And what you can do to make it a little more compact, since they're both over 21, is make it a single fraction. 3t minus 4 to the 7th minus 20 over 21. And then the sine and arc sine, since they're inverses, they cancel each other out. So you get v equals arc sine t minus 4 to the 7th minus 20 divided by 21. Now we've got our answer. Notice if it was cosine, we'll say it was cosine v, then we would take the arc cosine. If it was tangent, we'd take the arc tangent, and so on. Because what these do, arc sine, remember, sine gives you 3 pi over 2 is negative 1. If you took the arc sine of negative 1, it would give you back 3 pi over 2. It reverses what sine does, which is why they cancel each other out. And that concludes the notes for AP Calculus on the topic of trigonometric integrals.